What's up, guys, and welcome to this new series. Okay, this is going to be a one video series. So I'm only doing one video on this section. We're doing momentum and elastic collisions, as well as inelastic collisions, actually. Okay, as with the start of any section, we need some definitions. Okay, so the first thing that we need to define is the law of conservation of momentum. Okay, so that's our first definition. Okay, so the definition goes that the total linear momentum of an isolated system remains constant. Okay, and our formula for momentum is denoted by the symbol P. Okay, so momentum P is equal to mass times our velocity. Okay, and it has units of kilograms meters per second. Okay, remember mass is kilograms and velocity is meters per second. So units of kilograms meters per second. Okay, so if we want to understand the conservation of momentum, the total linear momentum of an isolated system remains constant. So what that means is that the momentum before a collision is equal to the momentum after the collision. Or we can expand this and say, yeah, okay, basically let's leave it at that for now. Okay, then another definition that we need is elastic collision. Okay, so what is an elastic collision? Okay, so an elastic collision is a collision in which both momentum and kinetic energy is conserved. Okay, so basically you go through a collision and momentum and kinetic energy, so P and EK, is conserved. Okay, and then lastly, obviously if we have elastic collisions, then we also have inelastic collisions. Okay, so an inelastic collision is a collision in which only momentum is conserved. Okay, conserved. Okay, so we can say that P is conserved and EK is not conserved. Okay, so the difference between a elastic and an inelastic is that in elastic, momentum and kinetic energy is conserved, whereas in an inelastic collision only momentum is conserved. Okay, so I have two examples here. Both of them are not very nice examples, as in they incorporate a lot of things that you guys would have learned. So if you haven't watched the mechanical energy videos, then you'll probably need to watch those before you can attempt these questions. Okay, but I'm going to assume that everyone's watched those, so we are going to go into example 1. Okay, so I'm going to set up the example. Okay, so basically we have a slope at 45 degrees, and we have this length right here is 1,5 meters, and this height right here is equal to 50 centimeters. Okay, we have a box at the top, and we have a bigger box at the bottom. Okay, the box at the top has got a mass is equal, let me just put the mass in it. So we have a box at the bottom right here which has a mass of 0.2 kilograms, okay, and the box at the bottom has a mass of 1,2 kilograms, and we can say the slope is frictionless. And basically what happens is the 0.2 kilogram box, okay, the 0.2 kilogram box slides into the 1.2 kilogram box and they collide elastically. Okay, so another note is collision is elastic. Okay, so that's another piece of given information. Elastically, yeah, so this box is at rest initially, and the box at the top is at rest initially as well. Okay, so we start off with the first question, question 1, which you can say calculate the potential energy of the 0.2 kilogram box at the top of the slope. Okay, so basically we know that EP is equal to mgh, which is equal to mass, which is 0.2 kilograms, times our gravity, times our height. Okay, it has 50 centimeters. Okay, we need to convert centimeters to meters because our SI unit is meters, so that's equal to 0.5 meters. Okay, and if we plug this into our calculator, what we get is, let's see, 0.98 units of joules. Okay, yeah, okay, cool stuff. Then the second part of the question says calculate the velocity of the 0.2 kilogram box at the bottom. Okay, so how are we going to do this? Okay, so again, we are using conservation of mechanical energy. So the mechanical energy at the top must be equal to the mechanical energy of the system at the bottom. So what we have is EP at the top plus EK at the top is equal to EP at the bottom plus EK at the bottom. Okay, taking our datum here. Okay, so if we take the datum from there, then our EP at the bottom goes to 0. Then what we're left with is, okay, we also know that at the top it's at rest, so that means our EK at the top goes to 0 because our velocity is equal to 0 and our height is equal to 0, respectively. So what we know is EP is mgh is equal to a half times mass times velocity at the bottom squared. Okay, masses cancel, so we can say that the velocity at the bottom squared is equal to 2 times 9.8, 2 times 9.8 times the height of, okay, so basically what we actually calculated already, but I might as well do it. Okay, so VB is equal to, if you plug that into our calculator, VB squared is equal to 9,8, so we square root both sides. So the velocity at the bottom is equal to 3,13 meters per second. Okay, remember we want velocity, so at the bottom here, it's going to be going towards the right. Okay, so that's our answer to that question. And that's our answer to that question. Okay, so the third question is where things get ugly, which we can say is calculate the velocity of the 1.2 kilogram block immediately after the elastic collision. Okay, so Another key piece of information is the word elastic there. Okay, so we're going to start off with conservation of momentum. Okay, so using conservation of momentum, we can say that the momentum before the collision is equal to the momentum after the collision. Okay, so the momentum before is going to be the mass. I'm going to call this block 1 and this block 2. Okay, so the mass of block 1 times the velocity of block 1 plus the mass of block 2 times the velocity of block 2. Okay, all of this is before and all of this is before the collision is equal to the mass of block 2 times the velocity of block 1. Okay, and that is all after the collision, plus the mass of block 2 times the velocity of block 2, and that's all after the collision. Okay, then we know that, okay, so this analysis that we're doing is from this point to the end, right? It's from this point where the velocity is equal to velocity of 1 is 3.13. Okay, and the velocity of 2, so this is before the collision, velocity of 2 before the collision is equal to 0 because it is at rest. So this term here goes to 0. Okay, so then we can say that 0.2 times our velocity was 3.13 is equal to 0.2 times the velocity of 1 plus 1, 2 times the velocity of 2. Okay, we don't know what these velocities are because it's after the collision, right? So if we plug this into our calculator, then we get 0,626 is equal to 0.2 v1 plus 1.2 v2. Okay, I'm going to divide everything by 0.2. So 3,13 is equal to v1 plus 6 v2. Okay, and I'm going to call this equation A. Okay, so that's as far as I can go. I don't know what the velocities are. I can't go any further. So now what I'm going to look at is this elastic collision part. Okay, so elastic collision. P is conserved, we've already dealt with that, but EK is also conserved. So what we have to do is we have to say that the EK before the collision is equal to the EK after the collision, right? So what we're going to have is half mass times velocity of 1, half times mass of 1 times velocity of 1 squared plus half m1 m2 v2 squared. All of this is before the collision is equal to a half times mass 1 velocity 1 squared after the collision plus half times mass 2 velocity 2 squared all after the collision. Okay, again we know this term goes to 0 because the velocity at 2 is equal to 0. So what we're left with is a half times 0.2 times the velocity at 1, which is 3.13 squared, is equal to a half times 0.2 times v1 squared plus a half times 1.2 times v2 squared. Okay, so time to work on our calculators. So if we plug this in, what we end up is 0,9797 is equal to 0,1 v1 squared plus 0,6 v2 squared. Okay, now what I'm going to do is divide everything by 0.1. Okay, so what we're left with is 9,797 v1 squared plus 6 v2 squared. Okay, so now this is equation B. Okay, so if we look at these equations, we have two unknowns and we have two equations. So what are we going to do? What we're going to do is we're going to manipulate this equation. Let's do it in a different color, purple. Okay, so 3, 1, 3 minus 6v2 is equal to v1. Okay, so now I'm going to say 9,797 is equal to 3, 1, 3 minus 6v2 squared plus 6v2 squared. Okay, so now we have one unknown and two equations. We've got one unknown, which is v2, so we can solve for this directly. Okay, so I'm going to do this on my calculator very quickly, but if you guys don't know how to do it on your calculator, then you're going to have to multiply this out. Maybe I should do that as well. Okay, so v2 comes out with an answer of 0,894 meters per second. It came out positive, so it is going to the right. Okay, so if you didn't know how to do this on your calculator, then you just have to multiply this out, this bracket right here, then you're left with v2s, and you can deal with that from there. Okay, let me just show you the step just in case. I know you guys should know how to do this. Plus 36v2 squared plus 6v2 squared. Okay, so you can group these together. This can move to the right hand side, and now you're just left with a quadratic equation. Okay, and if you solve this equation, you should get that answer right there. Okay, so that's basically the first example. So like I said, this last question is where things get quite ugly, but everything's manageable. You just need to know what you're doing. Okay, so let's move on to example 2. Okay, so example 2 is a bit of a strange one. What we have is we have a wall, or ceiling rather, okay, where we have a magnet connected here. Let's do the magnet in gray. Okay, so we have a magnet connected here, and the magnet is 20 kilograms. And what we have is another magnet on a table. So we have some kind of table right here. Okay, my art isn't very good, guys, sorry about that. But we have some table here, and the mass of this magnet is, let's say, 30 kilograms. Okay, so what we have is this pendulum kind of thing that's happening, and basically this thing is going to swing. Okay, so it's swinging, then it meets this magnet, they combine, and then we have it moving together. Okay, so when it swings down, hits this magnet, connects, and they swing together. Okay, so that's just for you guys to understand what's actually happening. Okay, and let's say the height over here is let's say 5 meters. Okay, so basically what we want to know is we want to know, calculate, let's put it in blue, how high the magnets swing after the collision. Okay, so basically what's happening is this thing swings, hits there, and then swings upwards, and we want to know this final height. Okay, so we want to know the final height where both magnets are connected. Okay, so first of all, we need to know the velocity so we need to know the velocity of the 20 kilogram magnet at the bottom. So how are we going to do that? We are going to go ahead and do conservation of mechanical energy. So E mech at the top is equal to E mech at the bottom. Okay, so I'm going to assume you guys, okay, this is at rest at the top. I'm going to assume you guys are quite smart, so we know at the top there's only EP, and at the bottom there's no EP, and we're only left with EK. The bottom. So what we have is mgh is equal to a half mv squared. Okay, and it's cancelled, so v is equal to the square root of 2gh. So that's equal to the square root of 2 times 9,8 times the height of 5 meters. Okay, so the velocity of the 20 kilogram block at the bottom, let's say this is place 1, this is place 2, and this is place 3. So at the bottom would be at position 2 is equal to the square root of 2 times 9.8 times 5, which comes out as 9,8995. Okay, let's just say 9,9 meters per second. Okay, cool stuff. So if you don't know how this step came about, do it the long way, but I'm just going to assume that you guys do know what happened there. Okay, now we need to know how much their combined velocity is. So how much is their velocity combined? So after the collision, what is their velocity? Okay, so we're looking for the combined velocity. So what we're going to use is conservation of momentum. So we're going to say that the momentum before the collision is equal to the momentum after the collision. Okay, so this is also at rest initially. So what we're going to say is that mass 1 velocity 1 before the collision plus mass 2 velocity 2 before the collision is equal to mass 1 plus mass 2 velocity after the collision. Okay, why have I said it's mass 1? Why is this correct? And why is this equation not equal to mass 1 velocity 1 after plus mass 2 velocity 2 after? Okay, so this is not correct. Okay, so the reason for that is because we know that after the collision, these two things are moving together. Okay, these two blocks are moving together as one system now. They're no longer two systems because they are magnets and they've connected. Okay, so we have to use this mass 1 plus mass 2 both traveling at one velocity. Okay, so we know that this term goes to 0 because it is at rest initially. So then what we're left with is mass 1, which was 20 kilograms. 20 kilograms times velocity 1 at the bottom, which is 9,9, is equal to, okay, I've obviously taken this as mass 1 and this as mass 2, is equal to mass 1 plus mass 2, so that's 20 plus 30 times velocity at A. Okay, velocity at A is the only unknown, so we can solve for this. Let's put it into our calculators, and the velocity at A comes out as 3, so the velocity after the collision, or their combined velocity, is equal to 3,96 meters per second. Cool stuff. Now the last thing we want to know is this height. Okay, and we know when it gets here, the velocity at the top is equal to 0. Okay, so what we're going to do is we're going to go back to our conservation of mechanical energy and say that the mechanical energy at the, let's start off with the bottom, is equal to the mechanical energy at the top. Okay, so we have our combined mass, okay, so we have, okay, again, I'm going to assume that you guys know that we just have EK at the bottom is equal to EP at the top. So what we're left with is mass 1 plus mass 2, rather half mass 1 plus mass 2 times velocity combined squared is equal to m1 plus m2 times g, so that's mass, gravity times height, which is what we're looking for. These two cancel, so what we're left with is our height is equal to a half v combined squared times g, divided by g. So this actually becomes 2g. Okay, so our height is equal to 1 over 2 times 9,8 times our combined velocity, which was 3,96 all squared. So if we plug this into our calculator, what value do we get? We get a height of 0,8 meters. That is our combined height. So that is the height we get to. This height here, it is 0,8 meters. Okay, so like I said, it's a very nasty question, especially if you guys aren't used to mechanical energy and momentum yet. So if you guys struggled with this question, try and understand what happened. So we wanted to get first the velocity of the 20 kilogram block at the bottom, so we used conservation of mechanical energy. Then over here we had a collision that occurred, okay, so we wanted to use conservation of momentum, and then we wanted to get the height, so we use conservation of mechanical energy once again. Okay, okay, let's actually go over one last thing, so because I haven't tortured you guys enough. So let's say so the question says, is the collision elastic? Elastic. Okay, so we know for the collision to be elastic, we already know that let's see, elastic, where's our definition? Elastic collision is momentum and kinetic energy is conserved. Okay, so we already know that momentum is conserved, right? So basically, we just need to show if kinetic energy is conserved. So we need to work out EK before the collision, and we need to compare it EK after the collision. Okay, so let's try work out EK before. Okay, so EK before the collision, okay, is going to be very interesting actually. It's going to be a half times mass 1, velocity 1 squared, plus a half times mass 2, velocity 2 squared. Okay, we also know that the velocity, okay, so before the collision is at the bottom right here, where this is at rest. Okay, so we know this term goes to 0. So our EK bottom is equal to a half times the mass 1, which was 20 kilograms, times the velocity 1 squared, which is the velocity at the bottom, which was this one right here, which was 9.9 squared. Okay, if we plug this into our calculator, we get the following answer: 980,1 units of joules, because we have energy. Okay, and then EK after is equal to a half. Remember, after the collision, these two things are moving together, so mass 1 plus mass 2 times the velocity combined squared, which is equal to a half, 20 plus 30, times the velocity combined, which we calculated as 9. Velocity combined is that one right there, which is 3,96 all squared. And if we plug this into our calculator, what do we get? We get 392,04 joules. Okay, so are these two numbers the same? No. So EK before is not equal to EK after, therefore collision is inelastic. Okay, cool stuff, guys. I think we've gone through a lot. Quite an interesting, quite a long video actually for this concept, but it's only going to be this video, so this is the end. If you want more practice on these questions, then you can go and do some examples from the IEB exams that I've uploaded. Okay, thanks for watching, guys. Yeah.